Hi everyone, I'm recording this video to show you my solutions to midterm 1. Okay, well the first question. Well, we want to prove that uh, n factorial is greater than n cube for a large positive n value. So this is the induction question. And for the induction question, well, remember there are three major steps. Number one, we want to find the start point. And in this question, I didn't give you the start point, so you have to try by yourself. You want to try n equals 1, n equals 2, n equals 3, n equals 4. And you will find that when n is 4, and then n factorial is already greater than n squared. Okay, so we can say, okay, n equals 4 will be the start point. And then the second step, we want to do a hypothetical assumption or inductive uh, assumption. That is, we assume that for a k value, and then k factorial is greater than k squared, and this k of course will be greater than 4. And then we want to prove that for the k plus 1 factorial, it will also be greater than k plus 1 squared, or k plus 1 multiplied by k plus 1. Okay, and then, well, how do we do that? Well, when we are doing the proof for the induction, we want to start from the really basic, really obvious part, and then we build on and on, and eventually we want to stop here. This is exactly what we want to prove, and this should be the last line of your proof. Okay, so I started from k is greater than 4. So, well, if k is greater than 4, and then this means, well, k minus 3, that is a positive value, and then k plus 1, that's also a positive value, right? Because k is greater than 4, and then we just multiply those terms in, and then we got k squared minus 2k, and then minus 3 is greater than 0. Okay, and then I want to move 2 from left side to the right side, so we have k squared minus 2k and minus 1 is greater than a 2. Okay, so if the value on the left side is greater than 2, and of course it will be greater than 0, and then I break this minus 2k into minus k and minus k again, and I move the minus k and minus 1 to the right side, so k squared minus k will be greater than k plus a 1. And then I want to extract 1k from the left side, so k multiplied by k minus 1 is greater than k plus 1. And then I want to multiply a k plus 1 on the both sides, so k plus 1, k, and k minus 1 is greater than k plus 1 squared. Okay, so why we want to stop here? On the left side, those are the first terms of the k plus 1 factorial. We have k plus 1 multiplied by k minus 1. And we can prove that for those three terms of the k factorial, they are already, the product of those three terms are already greater than k plus 1 squared. Okay, and then we want to multiply by even more values, 1 multiplied by 2 multiplied by 3, and then those values are positive, guaranteed. So if we multiply a positive value on the left side, and then this greater than will hold, and then we are able to prove that for k plus 1 factorial, it is greater than k plus 1 squared. Okay, this is my solution, and when I do the grading of your midterm 1, I see a lot of the interesting and smart solutions. So you don't have to follow my way, and then you whatever you are able to come up with. And well, this is the gap between n factorial and n cube that is really large. So you can come up with a lot of creative ways. Okay, and the next question: the best case of quicksort. And what's the best case? The best case is that we are super lucky and we have the median all the time. So we are able to do 50% to 50% partition, and then that is O in log n. And the worst case of the quicksort, we have talked about that. And then every time when we do a partition, and then we have 0 value on one side, and then n minus 1 values on the other side. So that's the worst case. So it will be n squared. And the best case of the insertion, well, remember we did this using some poker cards, right? And then we want to expand the sorted portion. We want to add one more value, and then we find that the value to be included into the sorted portion is already the largest value possible. And then for this value, the new value we want to add to a sorted portion, there's nothing to do. And then we expand again, and then we find the new value. The new value is greater than all the remaining of the values, and then okay, nothing to do. So in this case, for the best case of the insertion, actually it is a theta n. Well, what does that mean? It doesn't really mean anything, because if I give you a pre-sorted list and then I ask you to sort, and then it seems that the insertion sort is a winner, but it doesn't mean that the insertion sorter is a winner among all the sorting algorithms for any random input. So even though we say that for the best case of insertion it is a theta n, it doesn't mean that insertion sort is really the winner of among all the sorting algorithms. Okay, and for the merge sort it is O n log n, and you guys got this, most of you guys got this correct. And then the sequential search, well, we just visit all the values one by one, so this is a O n. And let me ask you this question. Why I say this is O n? Why didn't I say this is theta n? Did you notice that? Well, and think about that. Well, when we are doing the sequential search, we want to stop when we find the first value, right? If I'm looking for 10 and then I'm lucky, the first value I'm visiting, that's 10, and then I stop. Okay? So in this case, what's the cost? The cost is constant because I only visit one member. So the reason that we are saying this is O n is, well, in the upper bound, or the worst case, we have to visit all the values one by one, and then we stop at the very end saying, we don't have such a value. That's the worst case. And in the worst case, what's the upper bound? The upper bound is we want to visit all the values once each time. So that is a n times, but this is a O n. Okay, so and then since I didn't say that is for the sequential search, I didn't tell you it's the best case or the worst case. So saying this is a O n actually is the safer way, because we can still be lucky, right? And then for the binary sort, and I use the O again, and then but then we have the O log n, because, well, we are making use of the fact that the list is sorted, so we go into the middle, and then we decide, do we want to search on the left side or on the right side, but we don't have to do both. And then a primitive step, that is a theta 1, because that's a constant cost. And then for the heapify of a node, well, again, we have this issue. And when we are doing the heapify, and the worst case would be we heapify a root, and the root is a super small value, so we have to drag the root all the way down to the very end, or to the very bottom, to a leaf. And in this case, well, this is a log n. Well, but if we are lucky and we are doing a heapify of, say, a leaf, okay, and it is already a leaf, nothing to do, so this is a constant time. Or if we are doing the heapify of the root, and the root is already a super large value, larger than both of the children, and then again, nothing to do. So, well, this is the reason we say for the heapify this is a O log n, because if we are super unlucky, the cost will be a log n. But of course, if we are lucky, it could be better than log n. For example, it could be a constant time. Okay, and the next one, sorting. And most of you guys got this question correct too. And then the process will be, we want to do a selection sort. We want to scan through all the values, and then we want to keep the index of the smallest value. And the trick here is, well, you want to keep a record of the index of the smallest value. Okay, you want to keep the index, you don't want to keep the value of the smallest value, you want to get the index. Okay, and then eventually you want to do a swap. And does this algorithm sort the value low to high or high to low? And the answer should be low to high. And what is the best case of this algorithm? Well, it is, well, for the best, well, it is O n square. Well, this means there are two possible answers. Well, it is O n square guaranteed. And if the list is pre-sorted low to high, and then, well, that's a best case. And then for the best case, you want to argue that it is still a O n square. So, well, and in this way, another possible answer will be there's no best case because it doesn't matter this list is all random or pre-sorted low to high or pre-sorted high to low. Anyhow, it is a O n square algorithm. So whether we have a best case or not, it doesn't matter too much. It's not like this one. It's not like the best case of the insertion sort, because when we have the best case of the insertion sort, it will be a linear time. But for the selection sort, it doesn't matter if you have the list pre-sorted low to high or high to low or all random. Well, it is a O n square algorithm anyhow. And the next question is about the recursion. Well, for this question, for the 4a, and you want to do a proof of the solving a recursion using either substitution or a iteration. Okay, so either iteration or substitution. And in my solution, I did the substitution, and this is well, of course, you have to do more writing, but it can help you work out the Python. Okay, so this is my solution part, and then I want to figure out what is the t n divided by 2, and then I work on what is the t n divided by 2, and then I want to substitute this part to the t n divided by 2, and then I massage the output a little bit, and then I got 4 t n divided by 4, and then plus a 10n. Okay, originally I have 5n, now I have 10n. And I want to work on what is t n divided by 4, and I work on that on the right side. And after that, I got this, and I want to take this part and substitute the t n divided by 4, and then I work on this more, and then I got 8 t n divided by 8, and then plus a 15n. Okay, so after doing that for 2-3 steps, and I see the Python, and the Python is 2 powers k and multiplied by t n divided by 2 powers k, and then outside I have a plus 5k n. Okay, and then the next question I want to ask is, if I want to do this recursion on, and when do I stop? When can I get to the endpoint, the base case, which is t1 equals 1? So, well, when this value n divided by 2 powers k is 1, and then at this time k is log 2n. And after that, I want to substitute the k with the log 2n, and then eventually I will be able to prove that the tn is n plus a 5n log 2n. Okay, so this is a non-recursive version of the Tn, but our work is not finished. Well, I also ask you to prove that this is a O in log n. This is a omega in log n. So eventually, putting those information together, we are able to prove that that is a zeta in log n. So how do you prove that? Well, we can say, since this is n plus 5 in log n, and then this n is going to be smaller than n log n. So for this tn is definitely smaller or equal to 6 n log 2n. So I have a constant value, which is 6. And then for the n log 2n, that is the function f. This is function fn. So we say there is a start point, which is at 2, and then we have the cfn. Cfn will be the upper bound of the tn we just find. And what's the c value? C value is this 6. And what is the fn? Fn is n log 2n. Okay, this is a formal proof that for this tn, this is a O n log n. And similarly, we also want to find a lower bound. And for the lower bound, you can do a 4 n log n. So tn, which is n plus 5n log 2n, this polynomial is greater than 4 n log n, guaranteed. Okay, so I drop this in, and then I also reduce this 5 to 4. So this means we also have a lower bound, and for that lower bound, that is another cfn. And what's the c value? The c is 4. And then what is the fn? Fn is n log n, and starting from n value greater than 2. Okay, so this is a formal proof that for this tn, it is both big O n and then big omega n, putting those information together, and then we can finally say for this tn we just found, this is a zeta in log n. Okay, and then the next question we are doing a Pandomic strings. Well, you are going to receive a number of n, and I ask you to print all the possible Pandomic strings with the length of n. And by the way, well, I provide you the definition of the palindromic string. So a palindromic string is a sequence of the characters, and it reads the same either from one side or the other side. Okay. For example, BAB, that is the palindromic string because we can read that from left to right or right to the left, and they're all the same. Okay, and this is my solution. And my solution is, well, I want to create I want to create two set of the C's. And the reason I want to create two sets of the C's is, well, I don't know whether this n is going to be a odd number or a even number. So, well, I want to decide. Either way, I want to create a set of the seeds, no matter n is equal is even or odd. So if n is an even value, and then I'm creating a palindromic strings to be AA, BB, and CC, and the current length will be A2. So those those are my seed palindromic strings. And why I do this way? And see this hint. For this hint, if I have a seed as x, okay, and then if I add a to both sides, we have AXA. So we have the seed x, and then on the both sides I add a, and then AX A. Well, this is guaranteed to be a palindromic string as well. So starting from a set of the C's, and then I just expand and expand and expand, and I will be able to build palindromic strings with any length. Okay, and then after and for this function, I just depending on n is an even value or odd value, and then I want to create a different set of the C's, and after that I want to create another helper function called palindromic string builder, and then I'm sending my palindromic strings and then the current length, and then what's the endpoint? We want to end when the current length reaches to the end, right? And then, well, after I in this function, and then I want to for each of the strings in my current palindromic string, I want to grab that, and then I want to take one out, and then I want to put the current string as a seed, and then I add A's to both sides, I add B's to both sides, I add C's to both sides. So I'm throwing away one of my seed, and using that seed, I can build 3 more palindromic strings by adding A or B or C to both sides. Okay, and then I want to increase the current length by 2, and eventually, well, if the current length of my palindromic strings is exactly the same to the target length, and then I want to return my current set or current collection of the palindromic strings, and otherwise I want to do a recursive calls, and so I want to expand my current set of the palindromic strings again. Okay, so this is my my solution, and I did Python code, and if you want to do the pseudocode, that's also fine. Okay, and the last question, well, that's about the master theorem. And for the master theorem, we are going to start from a recursive definition of the Tn. And when you have the recursive definition of the Tn, you first want to grab 3 pieces of the information: a value, b value, and fn. Okay, so a is 4, and then b is 2, and then n is fn is n squared. Okay, and then the next part, what is the n powers log ba? N powers log ba is n squared. So now you have fn to be n squared, and the n powers log ba, that is also n squared. So those two, they grow the same. So they grow the growth of those two curves are exactly the same. So we are in case 2, and then well, for the case 2, that is n power log ba and then another log n. Okay, and then if I want to make it harder, one of the thing I can do is, how about this? Well, if I add a 5, and the answer should be exactly the same, because well, for this fn, for this fn, even though we have a 5 here, but we have the same degree of the polynomial, so the result will be exactly the same. Okay. And the next question is really a hard one. Well, we still have the a as 4, b as 2, and then fn now is n cube. Okay, and then we have the log powers n powers log ba, and then we have n squared. So in this case, we know that fn grows faster than n powers log ba. So that is case 3. But you cannot jump directly to here yet. You have to prove that given the information of the a and b and fn, well, you should be able to prove that a fn divided by b is smaller than a c fn. And for this c value, this c has to be smaller than 1. And can we really prove that? So let's plug in the a value as 4, and then n divided by b, which is n divided by 4, and then power 3. And then this is n cubed divided by 2. Okay, and then what is fn? Fn is n cubed, right? So we want to find a c value, and this c value is going to be smaller than 1, and yet this is going to hold. And then we can say, okay, if c is 3/3, and sorry, 3/4. Okay, if c is 3/4, and then we can say that a fn divided by b is smaller than c fn holds. As long as we can prove that it holds, there is a possible c value smaller than 1, and then we can jump to the next part, which is the conclusion. That is a zeta n cube. Okay, a lot of you guys missed this part, or you did this part wrong. Okay, the next question. Well, a, b, and they're the same. And then for this fn, this is n log n. Okay, and for the n log n, it grows slower than n powers log ba. So this is case 1. So for case 1, it will be zeta n powers log ba. So you have the zeta n squared. Okay, so those are my solutions to the midterm 1, and I have already finished the grading. And if you have any concerns about your grades and you want to ask me, can I still continue this course, or I should drop, or how can I better prove my grades, and feel free to come to my office hours, or shoot me an email so we can schedule a one-on-one time. Okay, so that's it for this video, and I will see you later. Bye bye.